Okay, so in this video, we're going to take a look at the the root test. All right, now the root test is kind of based on the idea here that if you take a look at the absolute value of the series terms, right, and if they are approximately uh, approaching some value rho, as you kind of see here, all right, that value rho, right, to the nth n plus 1, n plus 2 power after a certain value for n, right? Not necessarily from the beginning, but as n just gets larger and larger and larger, right? Then this almost looks like a geometric series, right? And we've seen how geometric series converges. That's kind of the theory behind the root test, right? So in our application here is we're going to take a look at the terms in the series and take the nth root, right, of the absolute value of the terms, right? So strictly positive terms. And we are going to calculate that limit, and we are looking for the limit to be between 0 and 1 for absolute convergence. Excuse me. If it is greater than 1 or infinite, an infinite limit, right, then we will say it diverges. And similar to the ratio test, if it is exactly 1, then it is inconclusive, right? We don't have any, we can't conclude anything here, right? And also keep in mind, right, in terms of the notation, when we talk about the nth root, what that means, right? So the square root of the absolute value of a sub n to the nth root, that's equivalent to absolute value of a sub n of 1 to the n, right? If we treat it as an exponent instead of the rational notation. All right, so let's work through some examples to see how this would work here. All right, so here, excuse me. All right. Okay, so here, let's see, we have our example here. It's going to be, we want to determine whether the series converges or not. We have n over e to the n. Right now, in trying to determine what is the best approach to find if a series converges or not, there'll be in some cases, some examples, right? There'll be different tests that are approachable, right? In some cases, right, one lends itself more to the other, right? Usually if I see like a factorial, for instance, then I always like to tend towards the ratio test, right? Just because that's how I'm going to be able to manipulate a factorial. Now, when you have something to the nth power, like you see here, then the root test might be a good candidate, right? Not always, but it can be, right? So in this case, we're going to apply the root test here. So we're going to take the limit as n goes to infinity. Now, all of these values are positive, right? So I don't need to worry about the absolute value. So I'm going to take this, and now it just becomes a matter of simplifying, right? The limit as n goes to infinity. Here, the nth root, so I'll write it like this, of n is n to the 1 over n. And in the denominator, the nth root of e to the n is simply e. All right. And now I'm going to focus on, well, how do I take the limit of the numerator, right? The denominator is a constant, so I can just write this as limit as n goes to infinity of n to the 1 over n. All right. So let's work on that. It's going to require our logarithmic logarithmic limit, where this will be equal to ln of L, right? And I'll focus here. Notice here we're going to have a L'Hopital's rule, limit as n goes to infinity, L over n, ln of n over n, right? Applying L'Hopital's rule, since they're both infinity over infinity, we get limit as n goes to infinity of 1 over n. All right, and so 1 over n over 1, just 1 over n, and when that goes to infinity, we get 0 equals to ln of L. So that means that e to the 0 is equal to L, or 1 is equal to L. All right, now be careful, right? That was not my total limit here, right? That's just going back to our original problem here. The limit up here is 1, but we still have that constant 1 over e. So the result of this limit is 1 over e, which is less than 1, right? E is approximately 2.1 something. So what that tells us is that by the root test, this series converges absolutely. By the root test. Okay. All right. So now let's do one more example here. Okay, so again, I want to determine whether the following series converges or diverges. In this case, I have n is equal to 1 to infinity of 1 plus 3 over n squared. Okay. Now again, whenever I have n in the power, I always want to think possibly root test. Again, not always, but it's a good starting point. Right? In case, especially if nothing else pops, gives you any ideas here. So I'm going to look at taking the limit as n goes to infinity. And here we have, what do we have here? So the nth root, and here I'm going to write this as 1 plus 3 over n squared, and I'm going to write it in the exponent notation. Right, and here I write it in the exponent notation because we don't get rid of the n in the exponent fully, but we do get rid at least of the squared exponent, right? Because when we have this notation here, we multiply those powers. So what this reduces to is the limit as n goes to infinity of 1 plus 3 over n to the n. Right, and it's a more approachable limit, right? This requires L'Hopital's rule, but before we need some logarithms, because here we have as n goes to infinity, it's of the indeterminate type 1 to infinity. All right, so looking at this here, so I'm going to take a look at the limit as n goes to infinity of n 1 plus 3 over n. Oh, excuse me, ln. One plus 3 over n equals to, say, ln of L. All right, and now rewriting it. So here we have infinity times 0, so I need to change it to the proper L'Hopital's rule by putting n as 1 over n in the denominator, and then 1 plus 3 over n in the numerator. Okay. All right, and now here we have as n goes to infinity, the denominator goes to 0 and the numerator. So you have 0 over 0. So now I can apply L'Hopital's rule. So we get the limit as n goes to infinity of 1 over 1 plus 3 over n. And then here, chain rule times negative 3 over n squared. And then here, down here we get negative 1 over n squared. All right, and then simplifying here, the limit as n goes to infinity, the n squares will cancel out the negative, so we get 3 over 1 plus 3 over n equals to ln of L. All right, now we let the n go to 0, so that 3 over n goes to 0, and this becomes 3 equals ln of L. So e cubed is equal to L. So going back here, that means that our original limit, as we calculate it, is e cubed, which is very much bigger than 1, right? E is about a little bit more than 2, right? So it's bigger than 1. So what that tells me is that by the root test, this diverges.